colleagues can join us. So last class where we left off was discussing about the steric demands of solvation around ether, and because of the other solvent molecules that are present, bulking this thing up. So for all the reason we were talking about that positive charge wanting to sit beta, because you need all these solvent molecules around it to stabilize that, you have the same thing with ether. Prefers this. So you tend to get this beta attack. So, sorry, alpha attack, because the ether sits beta. Now, one of the other things that we were pointing out, and I think what I left off with was, what about acetonitrile? Well, okay, so before I move on to that, what other solvents do this? Ether's not unique. So anything that kind of adopts this kind of system, anything with these kinds of oxygens can do this. And so the guiltiest subjects are ether, and that's going to be the one that we're probably going to see the most. I'm going to kind of stick to it, and you'll see that it gets used an awful lot in carbohydrate chemistry. THF, right? Same thing. Same kind of idea, except now it's like cyclic ether, basically, is THF. It's diethyl ether if you tie the two ethyl groups together. And then 1,4-dioxane is the other one that you'll often see. And the nice thing about dioxane is everything is soluble in dioxane. And so it's kind of if you have two ethers and you've cyclized them. So, but, you know, it's not really any different. DMF also tends to do this. Slightly different mechanism. Okay, completely different mechanism. But same kind of idea of the oxygen will chelate to that anomeric center. You'll get an M+, and that will try and be stabilized by other DMF molecules. And that will refer to CYT beta. Okay. Now, acetonitrile is different. I'm going to start a new page for acetonitrile. Well, I'll finish my thought on this one. So if we have this guy, sorry, we're going to go back to our oxocarbenium. And we did this in acetonitrile. And remember that acetonitrile is N triple bond carbon methyl group. And it's completely linear, which is kind of cool. So it's a lot smaller. Like, again, one of the problems with the ether is you got these wavy arms going freaking everywhere. And acetonitrile doesn't have that. It's linear. It doesn't have these wavy diethyl arms. And so it doesn't have the steric demands. And so it pretty cleanly attacks alpha. And because it's so much smaller, you're not going to need a lot of acetonitrile molecules to stabilize it. They're not going to take up as much space. So this is lecture 6, by the way. I skipped that slide. So in this case, now the Anomeric effect dominates. Yes. Okay. So what's going to happen next? Well, if you think about that and you have the anomeric effect there and your nucleophile is in there, again, just like with ether, what we expect to have is we expect to be basically setting up, an equilibrium between acetonitrile staying close and acetonitrile forming the bond. And if you need, here I'm using a dot, that means a carbon, if you don't remember that. I just really hate, just drawing a C there is really ugly. But it is implied because you have triple bond moving to a single bond. But if you want, you can add a dot. You're going to have to move. I need to turn a page. Sorry, my cat's sitting on my notes. I forget Zoe. Come on, sweetie. I'm sorry. I'm really sorry. Yeah. Okay, there's nothing like trying to pick her up to get her to run away because she really hates that. She could. I'm not sure how much information you get with meep, meep, meep. But then again, I'm not sure how much information you get from what I'm doing either. So maybe it'd be a wash. So whenever anyone's able to get a crystal structure of this, because you can, right? You can take the sugar, you throw in acetonitrile, you freeze it, and you can freeze out the acetonitrile sugar construct. And that's been done, and you can get a crystal structure. You never see beta. So this is actually very strong evidence. Oh, I lied. I was going to give you some readings about the reverse anomeric effect, and I never delivered. I will deliver that. Then that's going to be because I screwed up. That's your homework for next weekend. I like how nobody reminded me about it. Okay. But that's. Oops. Sorry. I'm going to just. Yeah, sorry. One moment. Sorry, this is things happening. Okay. So very strong anomeric effect, but it's even stronger than you. Man, I've got a digression. I'm gonna have to cut this out like in Camtasia or something. But it's stronger than we'd expect, and the selectivity is stronger than we expect. And so there's a proposal. I'm actually going to put this paper in the Dropbox, and I'm going to call it the acetonitrile network effect. And this is actually something I'm really interested in. And it was actually the first project I started here at Windsor when I came, was to try and demonstrate that this was a thing or not a thing. And the idea is that, well, let's think about this molecule. And there's more acetonitrile left nearby. So one thing that can happen is you can imagine acetonitrile attacking acetonitrile. What happens if we do that? Well, we'll have that. And then I'm going to draw a resonance structure of that. Well, I guess it's not a resonance structure because I'm going to move an atom, but still, just consider that guy. Okay. Now, if we have a nucleophile present, we'll stick with our nucleophile we've been using. And that's around. It should make sense that this might attack the carbocation. And now, of course, we move that positive charge onto an oxygen, which is quite a lot better than having it on the positively charged nitrogen. So that actually seems pretty favorable. We scrub away the hydrogen, and now we actually have a neutral molecule. But I've drawn this in a particular way, and you sort of see that it's kind of set up to do really a sigmatropic rearrangement. Where basically this acetonitrile solvent has delivered the ethanol to the beta face. And so this might explain exceptional selectivity. So this is one of these things where I used to really believe in this, because if you look in the literature, they'll all say acetonitrile is very, very selective for delivering nucleophiles beta. And this makes sense for explaining why. In my experience now doing a lot of this, acetonitrile is not really all that selective. So I'm less and less convinced by this explanation as time goes on. I'm less sure this is actually happening. But it's really pretty, and that has its own truth, because it is really beautiful, and I want it to be true. But I'm starting to think it's not, and that's really upsetting. So, I don't want to cry. So, to avoid crying, I'm going to move on. So, of these solvents, acetonitrile. So, what we have really is we have neutral solvents. These don't affect things either way. Our big one there is dichloromethane. but any of those kinds of chlorinated solvents are non-participating. So basically any non-participating. So these are your halogenated solvents. Okay, I'm just randomly erasing things now because my pen is acting up. We have the beta selective, and so that's acetonitrile. And there's another one that is actually beta selective as well, and that's nitromethane. And it's actually a similar, you can draw a similar kind of network kind of idea for it. I think I'm actually less convinced about nitromethane using a network. So that's where I'm really leaning towards. There is no network. It's all a lie, but I'll still post the paper because it's an interesting read. And then we have the alpha selective. And that was our ether THF dioxane. Okay. So those are the solvent effects. I want to talk about now temperature effects. So let's say we've got I've got ether on my mind, just ethanol. Silver. So let's say we have that reaction. We do it at 3 different temperatures. Pretend that you can heat dichloromethane to 80 degrees Celsius. You're doing it in a sealed tube. Magic. Suddenly, boiling point doesn't matter. And okay, let's say I give you a ratio of at 10 degrees and it is 64. Okay. So, if we get hotter than that, are we going to increase the ratio of alpha or the ratio of beta? Are we going to change? Is the ratio going to stay the same? Is the ratio going to change? And if it changes, is it going to favor alpha or is it going to favor beta? Like, is the number going to move more extreme or is it going to move towards parity? If we get hot, if we get hotter.
I'm just gonna take a guess and say that it'll shift towards the beta because it takes more energy to get there, I think.
Okay. Any other opinion? Susanna, you unmuted.
Yeah, I think it's gonna shift to beta also.
Okay, what's your
because
thinking?
it's gonna be more. Oh wait, no. I think it's gonna be alpha because when temperature increases, the stereoselectivity decreases.
Right, so you're already selective for alpha.
So,
Your logic is completely right, but you're picking the wrong thing. So I think you're going to
oh,
favor beta a bit more. You're going to move towards parity, right?
okay, yeah.
Because the stereoselectivity decreases. So you're right. You're both absolutely right, and I won't pick on Kirsten. So that's so what effect are we looking at here? We don't have a solvent effect present, right? We have a neutral non-participating solvent. We don't have anchiomeric assistance. We have a neutral. We don't have the ester here. We just have a ether. So this is purely the anomeric effect that's driving this ratio. It's why we're preferring alpha to beta. It's just the anomeric effect. So this is actually a question on assignment 1, if you've taken a look at assignment 1 already. And that's, what do you think about the anomeric effect being a kinetic or a thermodynamic effect?
Sorry, could you repeat that?
So is the anomeric effect a kinetic phenomenon or a thermodynamic phenomenon?
My guess would be kinetic. If we're still talking about, oh wait, no. Would be thermodynamic because then it's affected by temperature.
Well, kinetic, remember temperature, thermodynamic doesn't mean affected by temperature. Thermodynamic means, if we're thinking about thermodynamic effect, we're thinking about end state compared to starting state. Like we're considering state versus state interactions. And sort of stability of products. Whereas kinetics is the rate of reactions. And so rates are very affected by temperature. So I am going to say that there's one of the papers I put up in the Dropbox is from a few years ago, and by a few I think maybe 4 or 5, relatively recent, with somebody saying that there is no kinetic anomeric effect. I'm not sure I agree. I think actually the anomeric effect is mostly a kinetic process. I think it's occurring as, I think but you have an argument for it being thermodynamic as well. And it's kind of probably because it has an impact on both. But in this case, this reaction is more or less irreversible. Like once you make the product doesn't go back. And so normally if something is having a thermodynamic influence on a reaction, it needs to be part of a reversible process. And I would argue that right now this isn't reversible. So what's really determining this is, as the ethanol is coming in either alpha or beta, once it starts making that bond, as that bond starts to form, that's when it makes a decision to either make the bond or not. And if we're seeing a reduction of selectivity as we get hotter, then what that's telling us is that difference in energy, that difference in kinetic barrier matters less and less and less as you get to 80 degrees. Because it's just, as a fraction of the amount of energy in the system is basically negligible and it kind of gets washed out. So going in the other direction, if we lower the temperature, are we going to see more alpha or more beta? So we go down to 0 degrees from 10.
I would say that we'd see more alpha just because.
Perfect.
Okay.
Awesome. Congrats.
Yeah. Thank you.
So I think we actually go to about 82 under these reaction conditions. So eventually you kind of want to run these. So often what you want to do, what temperature basically emphasizes whatever other effects are going on. Cold temperatures. Other selectivity. That going is really messy. A bit too comfortable, maybe. So, okay. Yeah. So if we have beta selective reaction, like if we have acetonitrile solvent, cold temperatures will increase the beta selectivity of the reaction. If we have enantiomeric assistance, cold temperatures will increase the beta selectivity of the reaction. If we're relying on ether as solvent to get the alpha selectivity through an anomeric effect, or we don't have an effect like this dichloromethane kind of thing, then we're going to improve the alpha selectivity by lowering the temperature. And basically, all of this chemistry is a trade-off between getting temperature as low as possible, but still have the reaction go forward in a reasonable rate. And so that's always the trade-off in chemistry. Selectivity improves as you get colder, reaction rate improves as you get hotter. And so you need to find where that balance needs to be for what you need to do. Okay. So what we're going to do now is we've talked about 4 different things. And now I want to tell how to figure out anomeric selectivity. One, enantiomeric assistance. So C2 esters give beta. That's just a thing. It happens. It's almost inevitable. 2, solvent effects. So if you don't have enantiomeric assistance, then you look at solvent. 3, anomeric effect. If there is no real solvent effect one way or the other, then you're going to fall back on the basic anomeric effect of preferring alpha. For any electronegative substituent, but basically everything is electronegative, so I don't really need to. I don't think you can actually, because you can't have a nucleophilic attack with something that isn't a nucleophile, because then it doesn't do nucleophilic attacks. And for temperature accentuates all the above. Okay. So we're going to switch over to talking a bit about glycosylations. And I'm going to try and cut this shorter than I normally do, because I can actually quite happily go on about this for the rest of the course, and I am not going to do that as much as I want to just rewrite glycosylation again and again and again, because my pen is erasing everything. Okay. I'm going to underline a few times because we're going to spend the next little bit talking about it. So we've talked a lot about these anomeric bromides. How do we get them? Because start by drawing glucose. Sigh. Okay, I feel like throwing my pen through a window. Get another pen. This one's not sensitive enough, You can't win. What if I switch tips on my pens? That fix my problem? So we want to take this over to something that is, you know, something like that. And so there's a few things we need to consider. And one is, how do we install that bromide? How do we play around with this anomeric center to get things that are activating? And what kind of options do we have? And why do they matter? And why are there so many of them? And then number two, how do we play around with these other alcohols to get the selectivity we want? So we're going to talk a bit about both protecting groups and different glycosylation strategies. I'm going to come back to the protecting groups. We're going to start with just discussing some of the glycosylation strategies. And we're going to talk basically about how you can, roughly speaking, how you can design protecting groups for all of the different sugars and get everything free. The really, really good news about that is until a year ago, if you wanted to do this and kind of get a formal way of doing it, you'd actually have to sort of grab all my notes. And then I've got tons and tons of literature references and tons of individual papers on different ways of doing this because there's no central place for this. But somebody actually published a book on protecting group strategies in carbohydrate chemistry, which I'm really excited about. This is like the most exciting academic book because I was thinking about writing this myself, and then I saw that this other guy was writing it, and I was like, yeah, he's better than me, so I'm gonna not try and do that. But it's like, you get all these books at the library which are really specific for things, and normally it's like, yeah, I guess I need this for this, but this was like a book I was super excited about because I'm a real nerd. So we're going to come back to talk about protecting groups and how to decouple these things, but there's a handbook of carbohydrate protecting groups now. All that being said, we're going to talk about how to put that bromine on. So what we're going to start with actually is, I'm going to ask you to trust me that we're going to say how we can get here. We're going to start with beta glucose pentacetate. So it's beta, it's glucose, and it's got 5 acetates, so it's pentacetate. I am also going to call this peracetylated. Beta glucose. The per means everything is acetylated. So there's no everything, like the whole molecule, just all the alcohols are acetylated. So to stick the HBr on, the Br on, we treat it with HBr. It's in acetic acid as solvent because HBr is nasty shit. So you don't want to deal with neat HBr, so you deal with it as a solution of acetic acid. It's this super viscous, thick jelly oil stuff that is always this brown color, although they tell you it's clear and colorless and they're lying. So mechanistically, how does this happen? Well, actually, I'm going to open it up. Anyone have an idea of how this happens mechanistically? What's the first thing that probably happens?
Do we make our boat struck like with the
Sure.
oxygen ion?
Yeah, okay, let's do that. Let's make the oxygen. Yeah, both the oxocarbenium. That's what you're saying?
Yeah, that's what I meant to say.
Okay. Let's take this a little bit more stepwise then. Just this one time, I'm going to just take this really, really, like, almost irritatingly stepwise. I'm going to draw the upside down boat compared to how we normally draw the boat. And that's because I guess I should draw this properly. if I draw it this way, then the beta position now is almost pseudoaxial if I draw this boat. And so the lone pair on the oxygen, if we think about what that acetate looks like, it looks like that. And we have HBr, which is really a source of H+. So we can imagine this taking the H+. If we do that, then we have suddenly a good leaving group, right? Because we can draw the resonance structure of that acetate group. So I'm taking advantage of just erasing things. I think if I was a master at, using a copy paste function on this, I'd be better. That lobe is a little confusing. So what we have is, and now the positive charge is moved to this oxygen. So again, what I've drawn here is the resonance structure of the acetate group when it's protonated with the H+ from HBr. That's a good leaving group because that's acetic acid. So this is readily going to leave. And then we have Br minus. Now, that's not really the very stable boat, so the boat tends to, that's the boat that we got from having the beta. That's going to tend to flip to the other boat. That'll give us the alpha, which is the one where I'm much happier drawing. It gives me many fewer feelings of dread. And we get primarily the alpha bromide. Okay, so the main problem with this is needs HBr. So if you have almost anything else going on in your molecule, that's going to rip your molecule to shreds. Like, it's just such a strong acid. It's like so destructive. So although this is actually the way that works really well with a molecule like this, with galactose pentacetate, if you have a more complex molecule, there's no way you can introduce a bromine this way. So we need gentler ways to introduce bromine. So let's think about, let's say we have a molecule like this. I kind of ran out of space there, but it's also across. So those are both. This is called an isopropylidine group, or an acetonide. It's called both. It's called an isopropylidine because it's an isopropyl, right? Carbon, 2 carbons. You're attached to the middle one, so it's kind of like an isopropyl kind of thing. It's called an acetonide because it comes from acetone, because that's acetone. Put a double bond on the oxygen on that carbon. It's that. So both it uses both those names. I use them interchangeably and don't really have a preference. These are acid sensitive. So there's no freaking way they're going to survive being hit with a HBr rock. So we need a gentler way to do this. And a way that works really, really well is this. So there's two reasons to talk about this. One is because it's a gentle way to stick on a bromide, which is still really important chemistry, although, not that many people use bromides anymore for a lot of this kind of chemistry. The second thing is because make us really think about the structure of sugars and what are they actually. So has anyone seen this reaction or this kind of molecule before? This kind of reaction before?
It sounds familiar. I think from 331. I don't remember
Yeah,
exactly.
I think it is. I think we actually did this in 331. You're right. I have no idea if you took 331, Kirsten, the intermediate organic chemistry.
I'm in it right now. So
Okay. Cool. That's good. And Suzanne, I think you've taken some intermediate organic chemistry class, but you weren't here.
Yeah, but I also don't know this.
Okay. So this is called the Apple reaction. So I'm gonna simplify this out, and I'm gonna just write ROH in the presence of CBr4, triphenylphosphine goes to RBr. And this is a weird freaking reaction. Mechanistically, it's really cool. I love it. So there's not a lot of things here. And what I can say is the alcohol on its own doesn't do anything with either of these species. So the first thing you have to do is you have to react these two guys together. Excuse my Lewis structure. So this I really find counterintuitive. I see that, and what I see is, oh look, it's a carbon attached to 4 bromines. That carbon is really electron poor. Let's attack the carbon, and that's wrong. That's true, it's really electron poor. But we're actually going to do this. We make a carbanion. That's a little nuts. But when you think about it, that carbon is now attached to 3 bromines. Those are all pulling electron density out of the carbon. They can actually stabilize that C- quite reasonably well. And now if you have that C-, it can do two things. I'd accept either, really. It can either decompose through alpha elimination, releasing Br- and making a carbene. But then you have to deal with the carbene, and that's more steps to draw, even though it is chemically possible and feasible. So instead what we're going to do is we're going to use it as a base. And then we're just going to take care of it, and we're not going to think about it again. What's acidic? We have alcohol. Maybe it's not the worst carbanion ever because it does have 3 bromines. Still, alkoxides are better. This molecule here is called bromoform. It's like chloroform, except it's bromine. Does the same thing. Can still put your friends to sleep if you don't kill them. Please don't put your friends to sleep with bromoform. That's what ether's for. So now we have a deprotected alcohol, an O-, and we have a P+. And hopefully somewhere in the back of your brain, you've got phosphorus loves it some oxygen. Phosphorus oxygen bonds and phosphorus oxygen double bonds are ridiculously stable. Like, I think the entire universe is trying to become triphenylphosphine oxide. So let's help that out a bit. Moving towards the end state of the universe by making an oxygen phosphorus bond. Now, we can note that phosphorus is making an uncomfortable number of bonds for an organic chemist. I start getting very nervous when my elements make more than, I don't know, 4 bonds. And right now phosphorus is making 5, but phosphorus is third row, so it's allowed. It's allowed doing weird things that make me uncomfortable. So I'm going to let that go. But what we now have is a neutral molecule. Which is good. So I'm going to just redraw this a little bit. And I don't know if you remember the Wittig reaction. What we really want to move towards, as I said, is triphenylphosphine oxide. So this oxygen and this phosphorus are already making a pseudo bond here because they really want to do it. And if we do that, then we can think of this being delta plus and delta minus, because the oxygen's donating its lone pair to make that new double bond. But if we're doing that, then this oxygen's pulling electron density from this carbon, and this bromine can pull electron density from this phosphorus. And because we have phosphorus here, we can make sort of a 4-membered ring, because we can actually make a 90-degree turn right here on this phosphorus bond, because it is naturally 90 degrees. That is the bond angle. So we're set up for bromine to attack that carbon, to break this carbon-oxygen bond to generate the oxygen-phosphorus double bond, which would then break the phosphorus-bromine bond, putting electrons onto bromine. So we follow that logic through. Oh shit, we made a bromide and triphenylphosphine. So this is how the Apple reaction works. So first of all, any questions about the Apple reaction? Cool. So there's a very similar reaction called a Gehrig iodination. I think there's 2 G's. And this uses triphenylphosphine and iodine. Mechanistically, it's almost the same. It's just, bromine is really nasty. Br2 is really, really nasty. I2 is not as nasty, so we can get away with using iodine. We don't need to use this iodine equivalent of CI4. You can use CI4, it's fine. But iodine's a lot cheaper. You don't really want to use Br2 for this because it's really toxic, and if you can avoid using Br2, you avoid using Br2. Anyways, so I'm going to leave that there as an exercise. It might not be a bad idea to work through that and just make sure it's basically the same principle. We're just using iodine I2 instead of CBr4. Okay, so we have this. But there's still something that's going on up here that I haven't actually addressed, and that's that we've got a wiggly bond, but this one's not wiggly. Sorry, I don't know why I drew beta, it's alpha. Sorry, brain fart. Because like that doesn't work. That's not wiggly. It is alpha. And what we notice here is effectively we are doing an SN2 on this center. I'm just going to highlight where that's happening. Right there is an SN2 on that carbon. So we expect to invert the stereochemistry of the alcohol when we're doing that. But that bond's wiggly. It's not beta, it's wiggly. So why does this only give us the alpha? Because we have a mixture of alpha and beta.
Is it just because of the way that the bromine's positioned in that reaction? It's going to attack from the alpha phase?
Well, let's just think about how that is. So let's say we had it actually looks a bit like that acetonitrile network we were just discussing. I don't know what I just did. If it's positioned alpha, it's going to attack. Like if this is alpha, it's going to attack beta. If this is beta, it's going to attack alpha. So this kind of gives us a clue that for whatever reason, this doesn't happen. Because we don't see any beta bromide.
I would think that it might have to do with is it the sterics of the phenyl groups with the epoxide ring, or the, I don't know if that's what it's called, but the ring with the two oxygens on C2 and C3, or connecting them. I don't know.
Close, but no. How do we get here? So we got here because, so let's say we had OH. This with the CBr3 minus went to O minus, whereas this guy went to O minus. So I've drawn these as distinct molecules. And they are different molecules, right? They're anomers of each other. Do these two molecules interconvert? Oh, come on, we talked about this. Think like lecture 1.
No.
Yes, they do.
They do? Okay.
Mutarotation. They're constantly interconverting. Constantly going back and forwards via the aldehyde. So that's going back and forth to that. That one's going back and forth to that. Ring closing the other way. So we're constantly ring opening to the aldehyde, ring closing to the alpha, ring opening, ring closing to the beta, ring opening, ring closing to the alpha. It's happening like this, every few nanoseconds to microseconds, somewhere in that ballpark. And we were talking about the ratio of these guys back at the beginning. It varies depending on the sugar, how much of it's alpha and how much of it's beta. Okay. Similarly, once we've deprotonated these, can these two interconvert?
Yes.
Yes. Very fast. Much faster than a neutral. Because you already have the O minus there, so the electrons just flow right in, make the aldehyde, kick out the O minus, come back in, remake the ring, constantly doing this. Okay. Which of those is favored?
Is it the alpha because of the anomeric effect?
Okay, let's think about the Anomeric Effect. So the Anomeric Effect wants low-lying sigma star, right?
Right, sorry.
So you want a good leaving group.
Okay.
So what would be the leaving group in this case?
Be the O minus, which is
Yeah, it'll be O2
bad.
minus, actually.
Yeah.
That's not a good leaving group.
Yeah.
So what we're actually having here is we're favoring, it is the Anomeric Effect. You're absolutely right, Paul. But it actually really disfavors the alpha here because it's really, really weak. So we've been talking about the Anomeric Effect using what's called, so far we've always talked about the exoanameric effect. And that's that effect that we've been discussing. And that works better for alpha than beta because the beta can't do it. You can't line up the orbitals, right? Because you can't get oxygen's orbitals to line up with this orbital here for this Y group. So you can't do that. Okay. But there's another anomeric effect, because of course there is, because screw you, called the Endoanumeric Effect. So let's just think about that for a second. And so where does that come from? Well, that comes from the fact that, nothing magical about, if we think about this, there's nothing magical about this CO bond versus that CO bond. So if we think about it, there's an antibonding orbital there. And then we've got, I guess this is coming out of the plane towards us, and there'll be one going back into the plane away from us. And then if this is an O minus, then it's got a third lone pair. And if we have a beta, nothing's stopping the beta also having an orbital that can line up with this antibonding orbital. So this effect works whether the substituents are alpha or beta. guess there'll be one there. So this is the Anomeric effect. The external substituent has donating density around space the sigma star of C1 O bond, O ring bond. So we're donating into that CO bond, and so you get both that from both the alpha and the beta, and they're both actually pretty good at it. So there's no, it's kind of a wash. The endoanumeric effect doesn't actually get discussed very much because it's about the same alpha or beta. The only time it will be a little bit different is if for whatever reason you have some sort of ring or something's happening on the outside that's really restricting the way orbitals can align. But generally with normal things, it doesn't matter because you have the same amount of it coming whether your substituent is alpha or beta, because you can have that same overlap. But so the anomeric effect is equal on all of those. But we have a bad alpha anomeric effect. If anything, actually, it's reversed, where this guy's donating more than it's receiving. Because normally we have a good electron withdrawing group there. Here we don't. We actually have a really electron donating group. And then we have all the same problems of steric demands of charge. Must be stabilized by solvent. Take space. Bad. So, in general, I need more slides. Sorry. Keep. Home. So in general, and we've gone back to red. We prefer to have negative charges beta. So if we think about what's going on, going back to the apple reaction, you got two things. First of all, you have the equilibrium lies towards the beta, and then once you have a beta negative charge, it reacts faster than alpha negative charge because it's less hindered. There's more angles for the electrophile to approach that nucleophile. So everything's kind of playing that way. Both the thermodynamics of the system, the equilibrium lies towards the beta, and the kinetics of the system, the beta reacts faster because it's less sterically hindered. So the beta wins no matter how you look at it. And so for that reason, we kind of set up an equilibrium system like this. where of course fast and slow are relative terms. This reaction is fast no matter how you look at it. But we have this system where everything is funneling our material towards this top product. Right? Because we have both this equilibrium and these rates favoring this guy up here. And so this comes down to kind of making use of the fact that we can take advantage of, hey, there's this anomeric effect thing going on. We know about that. We know where that charge prefers to sit. It takes up space because it needs to be solvated by everything else. So it's going to prefer to sit beta. And then if it does sit alpha, which is unlikely because now we have a really weak anomeric effect as well because we can't really accept electrons. We already have too many freaking electrons. Then we're now crowded because we have this effing ring blocking half of our angle of attack. There's a ring sitting over, like there's a ring here that is blocking the attack from this whole top bit of this oxygen. Whereas this guy, basically, you can't attack from this low cone angle here, but that leaves almost all of the space available for it to react with. So, everything favors beta. Beta phosphonium. It's not a phosphonium. I'm gonna call it phosphine star because I have no idea what the functional group is called. Everything favors that, therefore get alpha bromide. Talked about that. Okay, I think I'm going to leave it there for today. I think when we're going to come back to this tomorrow or Thursday, we're going to talk about how we can favor alpha versus beta on the reaction products of these kinds of bromine reactions, and then how we can kind of play with these things. And then we're going to switch over to talk briefly about some anomeric fluoride chemistry, because that's kind of the safer version of this. They're more stable. The problem with these bromides is you can make them, but then you look at them wrong and they decompose on you. So they're not really storable. They're not really, can't carry them through transformations. They're very reactive. The nice thing about a lot of the other groups we're going to talk about, so we're going to talk about fluorides, we're going to talk about sulfur activating groups there, and then two other kind of orphan ones, which I just really like because, you can tell I like mechanism. So one of them is trichloroacidimidates, and the other one is this weird thing that you get with double bonds. So we're going to talk through those and see the advantages and disadvantages of these different glycosylation strategies. But we'll start with fluorides next class after we finish up bromides.
Would you be able to talk about the Endoanumeric effect again?
Yeah.
I just got kind of confused.
Yeah. So, because I did pass over it really, really quickly. That's absolutely fair. So let's say we have a normal molecule, a normal alcohol like this. There is an endoanumeric effect. And so if we think about this is a sigma. Shit, I did this again. Okay, let's see if I can. And it's going to take me longer than I thought. Okay, just pretend that up is down and down is up. This is up there. There's also a sigma star orbital where we have the antibonding orbital of the weakest bond in a molecule. The weakest bond in this molecule are these acetal linkages. And so far we've been focusing on this one, the external bond. But this is also a carbon-oxygen bond. It's also pretty similar. So if we think about what that looks like, we have that. Now, of course, we have no electrons in it because it is an antibonding orbital. But what that means between that carbon and oxygen, if we did have electrons in there, UV orbitals form when that oxygen and carbon sp3 orbitals come together to make the new bond, and we have two sp3 orbitals coming together, so they create a sigma bond and they create a sigma star. It's conservation of orbitals. You have two orbitals coming into the interaction, you need to have two orbitals coming out. It's just each of those sp3 orbitals that make that oxygen-carbon bond have one electron in them, and they can both go into the bonding orbital. And that's just how bonds are made. That's how all bonds are made. Cool. Okay. So the antibonding orbital looks like this. The geometry of that is, I can draw the big lobe on the oxygen going back into the page. And then I guess we'll shade those in. But we have lone pairs on this adjacent oxygen. And again, we want to always delocalize electrons. And so the electrons, if they can, want to delocalize into that antibonding orbital. And there's nothing stopping them. Because what we can do is this can orient itself such that one of its lone pair is also coming out of the plane towards us, lined up with this big juicy sigma star. The other lone pair, I guess we could put it back into the plane, which would then put the H up here if I want to draw that properly as a tetrahedron. But this lone pair here, like, it's arbitrary which way I'm shading that, right? So maybe I'll unshade that and I'll shade. I just don't like shading to wash into the page once. But these electrons can donate into this orbital. So we have donation of oxygen's non-bonding electrons into the sigma star of the C1 O-ring bond. And that's a stabilizing interaction, right? Because we are delocalizing electrons. And so some of the electrons are going to delocalize into that. And so that is going to lengthen out this carbon-oxygen bond a bit. Now, normally, if we have an OH there, the opposite effect is stronger, donating into that. Now, of course, with the beta, we can't have that. With an alpha, we do. So for the beta case, that CO bond has some double bond character. It's shorter than you expect. And this is the opposite of the alpha. And the reason so in the beta case, all you've got is that endoanameric effect, where you're donating electrons from an outside oxygen in, because the lone pairs on this internal oxygen cannot orient themselves to line up with the antibonding orbital of this CO bond. But you do get that with the alpha. But you also have this oxygen donating in. So why aren't they even? Why don't they cancel each other out? Well, that's because, let's think for a second, this oxygen is more electron rich. And that's because this oxygen is attached to 2 carbons. This oxygen is only attached to 1 carbon, and carbons are electron donating relative to hydrogen. And that's what this oxygen is attached to. So this oxygen has 1 donating, 1 nothing. This one has 2 donating. So that means this has more electrons than that one. So the flow goes from the ring oxygen to the external oxygen when you have alpha. When you have beta, you can't go from the ring oxygen to the external oxygen. So the only anomeric effect you can have is from the external oxygen in. And it's a much weaker effect because, again, this is a electron poor oxygen, so it's less likely to donate electrons. But it's still possible to do. Did that help at all, Paul?
Yeah, that helped. So, like what we were saying before when we had that O- was that it had like a bad anomeric effect, but it had a bad exoanameric effect, but it had an okay.
Yeah,
like,
very good endoanumeric effect. Yes.
Okay.
Yeah.
Okay. Thank you.
Yeah, you're welcome. Okay. I will talk to all of you guys later. Have a good day.
Thank you. Have a good night.
So,
Yeah, you too.
bye.
Bye, everybody.